Hi everyone, I'm Julia. I'm a product manager at MongoDB focusing on developer tools, specifically MongoDB Compass and Atlas Data Explorer.
And I'm Shelby Carpenter. I am a senior product marketing manager at MongoDB, where I focus on all things developer experience, including our developer tools and our programming language communities.
And today we're going to talk about how to accelerate your development with MongoDB, specifically using our MongoDB developer tools. So first we're going to talk about this idea of proactive performance management, what it is and why it's important. Then Shelby will talk a little bit about how you can decide when to index. I'll talk about how you can optimize your index usage to make sure you're getting the most out of it. And then we'll close with some best practices and final thoughts. If we have time, we'll do a Q&A. If we don't have time, feel free to follow up with Shelby and me directly. So what is proactive performance management? Simply put, it's just accounting for potential performance issues before they actually become a problem. This often means considering performance and addressing problems before they manifest during the development phase. For this talk, we're going to specifically focus on your indexing strategy. So having an effective indexing strategy informed by the queries that you're planning on running is really important for your application performance, especially when you're working with large data sets, which I'm sure many of you are. But unfortunately, what we see is that many developers wait until there's already a problem to develop their indexing strategy. This makes sense. If you're looking at resource consumption or query execution time, but you're developing with a really small quantity of data, it might not look like there's a problem, but it doesn't necessarily mean that your query is performant. What happens as a result is that when you are working with larger quantities of data, you experience performance issues, maybe in production, it becomes very stressful or even risky to fix. But it does not have to be like this. So what if you could anticipate your performance and optimize your indexing strategy before there's even a problem? The good news is we can do this, and we're going to talk about how MongoDB developer tools can help. So, Shelby and I are building an app. It's a weather app, pretty basic. We're just doing some CRUD operations, and we're using MongoDB, obviously. Our data is pretty standard, but we have a lot of it. So we're collecting weather data from all over the world. We're collecting kind of summary statistics about the weather, like pressure, humidity, temperature. Luckily, we're not dealing with a complicated data model. There aren't a lot of references. We have a few nested fields, a few arrays, but nothing too deep. The really important thing to remember though is that this is weather data. So there is a ton of data. We're going to be writing to the database pretty constantly, and this is a consideration that will be coming up throughout the course of our discussion. All of this considered, Shelby, would you like to chat a little bit about how you like to develop with our tools?
Absolutely. So one of the great things about MongoDB is that we are a full developer data platform with a full suite of developer tools for how you might like to work with your data in the database. For me and my kind of character in our weather app drama, I really like a programmatic approach. I am a real hands on the keyboard type of developer. I don't want to use my mouse to click around in a GUI. So I really like to use the MongoDB for VS Code extension, as well as the MongoDB shell.
I'm not quite opposite to Shelby, just a little different. So I do actually prefer our UI tools. I like that the information is parsed and easier to read. I also like that I don't have to remember, all of the database commands, and it's pretty quick to get my tasks done in the UI. So I personally use tools like MongoDB Compass or Atlas Data Explorer. This considered, I'm going to pass it to Shelby, and she's going to talk about early indexing considerations.
Great. So one thing we can do to optimize our queries and ensure that we have a performant application is making sure that our queries are covered by the right indexes. Before we get into indexes though, I'd like to talk a little bit about how MongoDB queries work. So MongoDB queries are run with the help of an internal query planner. And what the query planner does is it looks at all of the potential ways that a query could be run, and it picks the best one for you. And there's a couple of different types of collection scan, different ways of scanning your data that MongoDB can do. One is a collection scan, or what you'll see as a call scan and explain plan output. And you'll see this when your query is looking at every single document in your collection. You might also see index scans or IX scan in your explain plan output. And this is when your query scans index keys when your query is covered by an appropriate index. So in general, in most cases, it makes sense to have your query be covered by an index. But the exception to this is when you have a write volume that is higher than a read volume, because it can slow down your writes. But if you're doing more reads than writes very consistently, in most cases, it's just going to make sense to have an index for that query. MongoDB has a number of different types of indexes, but what we'll talk about here are two of the most common types that you might want to use. So, if you are primarily going to be querying a single field in your collection, you're probably going to want a single field index. However, if sometimes you query multiple fields, you're going to want to think about having a compound index. And when you're building a compound index, I'd ask you all to try and remember what we call the ESR rule, because this is just a very helpful shorthand for how to approach this. When you are building a compound index, the ordering of your index keys is very important. And ESR can help you remember how to approach this. It stands for equality first, sort next, and range last. There are some edge cases where the ESR rule won't be perfect, but it does apply in most cases and is a good place to start. So one of the great things that MongoDB offers is an explain plan, which when you get it with the help of one of MongoDB's tools, will give you information about how your query performed. And you can access this through things like the MongoDB shell and through Compass. When you're interpreting your explain plan results, there's a couple of key pieces of data that you should look at. You're going to want to find where the winning plan is. So look at your query planner, winning plan, and then the stage. And you'll see if it was a call scan or an index scan, like we talked about earlier. And then you can also see execution stats. There's a couple of key pieces of data in here highlighted in green. There's n returned, which is the number of documents returned by your query. The execution time in milliseconds, so how fast or slow your query is running. And then total keys examined, if you did have an index and it's looking at those index keys, and total docs examined. All right, so we just covered a lot of general information about queries and indexes. Let's look at how this is all going to come together for building our weather app. So I'm building a couple of application features. I'm here in New York coming from California, and in California we had a very rainy, cold, if you're in the mountains, very snowy winter. So I'm ready to get some sunshine this summer, and I'm going to build a couple of application features to support that. The first one I'm going to build is called the Sunshine Finder, and this will let me look up cities where the weather is clear, where there's no cloud cover. I'm also going to build the Storm Finder, so I'm going to look up cities where the air pressure is low, which generally means that a storm is coming. So let's look at how we can approach getting the right queries and indexes for each of these two features that we're building. All right, so we're opening up the MongoDB shell and using our Atlas connection string to connect to our Atlas cluster. I'm going to choose my weather underscore data database, and I'll be using the cities collection. First thing I'm going to check is if I already have an index. Looks like we're indexed on the ID field, which is something that MongoDB does for you in every collection. So I'm doing a quick search to find places where there's no cloud cover. And it looks like the weather's good in a town in Great Britain and also in Ethiopia. So maybe some cool places I want to think about traveling to. So let's run that query again, but this time we're going to get an explain plan, which you can do with .explain and then execution stats in quotation marks. It produces a lot of output, so you do have to scroll up a little to find what you're looking for. But you can see that we did a call scan here, which makes sense because this isn't indexed yet. We have a large number of docs examined and returned, and it took 16 milliseconds, which feels a little slow to me for a simple query. So we're going to create an index for this. And then let's run our query again and look at our explain plan and see the difference. So when we go to our winning plan, we can see that now we have an index scan, which is what we would expect. And our docs examined to end returned is the same. And our execution time was 12 milliseconds. So we did improve it a little bit, which is what we're looking for. So we can feel good about having made some improvements to this query with the help of an appropriate index. Now we're going to do a more complex query. We're going to look in the US for weather pressure in a certain number of millibars and sort it by time. And looks like the weather's a little gross in Seattle and in Redmond, so I'm going to avoid those areas. And let's see how this query performed by getting our explain plan results again. So scrolling up again, and you can see that we had a call scan, which makes sense because we haven't created an index for this yet. It takes 20 milliseconds to run, and we examine quite a number of documents compared to the documents that we returned. So I have a feeling that we can improve this if we create the right index for it. So we're entering a compound index here so that we can improve the performance of this query, rerunning it and getting an explain plan back to see the difference. So you can see that we do have an index scan now, which is what we would expect. That was the most performant query that the query planner selected for us. Our docs examined to end returned is the same number, and execution time is all the way down to 4 milliseconds. So we made a big improvement there. We can feel good about having put in the right indexes to improve the performance of our queries for our application. Now I'm going to hand it over to Julia, who will talk a little bit about how to optimize your indexes once you already have them in place.
Thanks, Shelby. So I want to focus on something that Shelby did bring up, which is that in general, you do want an index for your most important queries. However, when your read volume or when your write volume is higher than your read volume, it complicates things. This is because although indexes speed up reads, they do slow down writes. This is a heavy consideration for Shelby and me because, as I mentioned, we expect that our application will be write heavy. Let's talk about why that's the case though. So, when there are no indexes on a database and you make an update, for example, you just write to the corresponding document. For example, I have this piece of a document from our data set and it has the temperature, but the temperature is in Kelvin. I do not know what to do with that information. If you tell me a temperature in Kelvin, I don't know how to address. So I want to update it to Fahrenheit. There are no indexes, so I just make the change in one place. I have to update the document. However, when there are indexes on a collection, you're not only updating the document, but you're also making a change to all of the indexes that have copies of that data. So in this example, we have the document that again has the temperature in Kelvin. And when we update temperature to Fahrenheit, we're updating the document, but we're also updating all of the indexes. This takes longer because we're simply doing more things. Now, this doesn't mean that we shouldn't build indexes on write-heavy applications. We absolutely should, but we need to be smart about the indexes that we do build. And there are a few ways to do that. We're going to talk through them. So right off the bat, I would recommend that we consider our workload. This means a few things. So one, what types of queries are you running? Are they single field queries? Are they multi-field queries? As Shelby talked about, that will dictate the type of index that you build. It's possible that you can cover multiple queries with a single index, and that's something that we'll talk about a little later. The next thing you want to consider is how often you're running the queries. If you're running multiple queries a second or a minute, you might want an index. It could put significant strain on your resources. However, if you're just, for example, running one long-running query overnight once a month for a report, maybe it doesn't matter if it takes a long time. You can decide whether or not it merits an index. The last thing to consider, well, one of many things, is how much data do you expect to access with your query? If you're querying on a small set amount of data, maybe you don't need an index. It will probably not put too much strain on your application. But if you expect that you'll be querying a lot of data or that the amount of data that you're querying will grow, you probably want to consider an index. But having an index isn't always good enough. You want to make sure the index is actually good and serving its purpose. So one way to do that is by examining index selectivity. So we want to index fields that are high cardinality. What that means is that the fields have a lot of different potential values. If fields have a lot of different potential values, there are more selective index results. Simply put, this means that when we're searching through an index, we're actually searching through fewer documents. Because we're looking at fewer documents, the queries are just quicker. One way to test whether or not a query and index are selective is by looking at the explain plan like Shelby demoed. So these are two examples of explain outputs of two different queries. They're both using an index, like they both have this index scan stage. But this doesn't mean that both queries are equally good. One is actually more performant than the other. And we can tell by looking at these two values, docs examined and end return. So in the example on the left, you can see that we had to look at over 2,800 documents to return one. That feels like a lot of wasted work. In the example on the right, where the index was actually more selective, I just had to look at one document to return one document. So I'm doing the minimal amount of work to get the result that I want. You don't have to be working with a lot of data to see this result. In general, you can just look at this ratio and it will be a good indicator of whether or not your query is performant. The last thing that I want to talk about before going back to our app building journey is removing index redundancies. So, like I said, working on a write-heavy application, we want to have the smallest amount of indexes possible to maintain a good performance across our queries. It's important to note that you do not need a unique index for each important query that you run. When indexes are structured correctly, you can actually take advantage of and even completely cover queries with indexes if the query uses a subset of the fields. So it's really important that we eliminate index redundancies so that we're maximizing the resources that we have available to us. The way that we can do this is by taking advantage of index prefixes. So an index prefix is exactly what it sounds like. It's an ordered subset of the index. And indexes can support queries that use all of the index fields or a prefix of the fields. So order does matter when you are creating an index. Let's look at an example. So say I have this index on top, which is on, country, the city name, and the weather. All of the example queries below are completely covered by this index because they're using the index fields in order. So, for example, city.country and city.name, they're using an index prefix. We should be able to get that one-to-one ratio with a basic find query. What would not work as effectively as we would hope, for example, would be a query on city.country and main.weather. In this case, we would only be able to take advantage of the fact that city.country is indexed and not the fact that the combination is indexed because they are not next to each other in the index prefix. That was a lot, but we'll go through an example. So like Shelby, I'm also developing some app features, but unlike Shelby, sun is not that important to me to go outside. I will go outside regardless of the weather as long as it's not too hot, not too cold, and definitely not humid. So I want to find the best places in the world to be outside. The more aspirationally adventurous side of me also might want to try some sky activities this summer. I don't really think I'll be flying an airplane, but I could go hot air ballooning or hang gliding. So temperature is important, humidity is important, but also wind speed becomes a factor. And because we're querying on similar fields, we have a lot to think about in terms of our indexing strategy. So let's take a look at what that looks like. So to start out, I've taken a very rudimentary approach. I have two queries, one for this outdoor use case, one for this sky use case, and I've just built an index for each of them. You can see that for my outdoor index, as I mentioned, I just indexed temperature and humidity because that's what I'm querying on. And for these sky activities, I've done temperature, humidity, but additionally wind speed. Looking at this, I think that I could probably remove an index redundancy by getting rid of the outdoor index because my sky index contains the fields that exist in the outdoor index. But let's look at how we can use Compass to confirm whether or not this is the case. So what I'm going to do first is just establish a baseline. I'm loading my outdoor query into Compass and running the explain plan, the visual explain plan. And it's working as expected. I see it's using the outdoor index on temperature and humidity. I'm establishing a baseline, so I see around 3,500 documents examined and returned, and also around like 4,400 index keys examined. This is just important so I can compare it to the results later. If this is working properly, I would expect that nothing changes when I remove this index. To actually test this out, I'm going to do something called hiding the index. Hiding the index doesn't actually delete the index, it just hides it from our query planner so we can kind of simulate an environment where this index doesn't exist. The reason that we would hide an index is that creating indexes is still resource intensive, so I don't really want to delete and rebuild one if I don't have to. So, all of this considered, I'm actually going to go into Compass, and we have an embedded shell, so I'm just going to toggle that open and run the hide indexes command. So, just a simple hide index. I name my query, so I can just type outdoor query, or index, I should say. Cool. And it looks like it worked. This is the expected response. I can see that it's now hidden, which is great. So just gonna run this query again with explain. And okay, I see that it's using the new index, which is good. I also see that docs examined to returned are the same, which is good. But the index key value is higher than expected, so this isn't actually performing the same as before, which is my first hint that something's off. I also see that the query execution time is kind of notably higher, so something isn't working as expected. What I actually think is happening is rooted in index prefixes. So if you look at the query that I've written, I'm querying on humidity and temperature, but they're not next to each other in the index definition. So this means that I'm really only taking advantage of the fact that main.temperature is indexed, and I'm not taking advantage of the fact that the combination is indexed. So I can actually do better here. What I'm going to do is actually build a new index where the fields are in an order so that I can take advantage of the index for its full capacity or potential for both queries. So process is the same. I'm going to hide the sky index now with the same process embedded shell, but I will demonstrate how to create a new index in Compass and confirm that it works for my query. So I'm now on Compass's indexes tab, and definitely keeping temperature there. But this time I'm going to make sure that humidity is next to temperature, so I have that index prefix that I can take advantage of to fully cover my query. And I'm adding wind speed because I also want to make sure I cover my sky query. Awesome. I just hit create. Nice, so it's created, and now the next step is to repeat the process and run explain. So I run explain on the query, and it is using the new query, which is great. Execution time is down, and now I see that docs return, docs examine is the same, but the index keys value is down as well. So I feel confident that this worked for me. I feel good. The last step is to just remove those two hidden indexes from my database so that they, aren't taking up space since I know that I don't need them. I go to the indexes tab, and deleting indexes in Compass is really easy. You just hit delete, and you have to confirm that this is what you actually want to do so we don't make any mistakes. So I'm deleting the kind of like sky conditions, and I'm going to do the same for my outdoor index. Cool. So I feel good about moving forward. I'm going to pass it over to Shelby to wrap things up.
All right. So throughout this presentation, we've learned a lot about how to optimize your query and index strategy with the help of MongoDB tools, especially Compass and the MongoDB shell. Let's talk a little bit about the real-life impact of this. So what you're seeing here is a screenshot from the Atlas UI looking at a series of queries run over a period of time with two different namespaces, green for one, red for the other. And on the y-axis, you have the execution time. You'll see a red dot kind of in the center, really up high, and then a lot of other dots that are far above the 1 second mark and a couple that are above the 2 second mark. this is extremely slow if these were queries that were running in a production environment with user-facing impacts. And these are the sort of things that lead to P0 engineering escalations. So this is not exactly what you want to see in production, and you can avoid this by planning out your queries and indexes in advance. And you can do this with the help of MongoDB tools, like we've talked about today. That's all we have for you. You have our information up here. You can reach out to either of us. I'm on Twitter. We're both on GitHub. I'll give folks a second to scan if they want to check out MongoDB Compass or the MongoDB shell. It should also be very easy to find later just by Googling them. And here's another place where you can also scan a QR code to give us feedback. We'd love to hear what you thought of this session. We're always looking to improve the experience at this event and keep you coming back next year. With that, I think we have a couple of minutes for questions. If folks want to raise their hand, we have someone who's kindly offered to run a mic around. We will need a mic because it's very loud in here. So just raise your hand if you have a question. Here.
Hi. This is about the index. As you mentioned, like we can hide the index, right? So in case of writes also, we can hide the index to make the performance better, or it only works for in case of reads only, hiding indexes.
Oh, I heard that it was about hiding indexes, but I actually can't hear very well. You wanna?
Yeah. So like when we have the indexes, when we try to write the data, it will take more time. That's a known thing, right?
Yeah.
But you said there is a hiding feature in indexes. So especially in case of select, if you want to avoid to use a particular index, you can hide. Same thing we can do in case of writes also.
Wait, I'm actually just gonna come closer to you. It's not you, it's that there's like a lot of noise over
A lot
here.
of ambient noise.
Thanks, Julia.
Yeah. Sorry.
Indexes we can hide, right? By selecting to avoid indexes in case of variances, right?
Yeah.
So same thing, can we hide the indexes to make the write performance better?
Okay, got it. So the question was about hiding indexes to make the write performance better, which I'm sorry. And it won't actually make the write performance better because the indexes still exist on the database. So it's not until we actually drop the index that we see the other performance benefits of it. That's a really good question. Cool.
Well, any other questions, just raise your hand. Looks like we have one over here towards the center. Thank you. Yeah, sprint.
Thank you. I thought you said earlier that when you had a write-heavy application, that there was a way to tune the indexes so that it still worked okay. I don't think you covered that. I don't think you answered your own question.
So the main point that we wanted to drive home is that we should just be really careful about the indexes that we create, and we don't want to create an index for every single query that we're running. So in this case, it would be just reducing the number of indexes we have when possible. But I will say we have some other features and different indexes that do help with really specialized cases where like maybe you have a write-heavy application but you want to do analytics, and like happy to follow up afterwards about that if that's something that might be relevant to you.
Not really. I was just curious.
Cool.
It's like we're mostly like everybody else. Everything is 95% read.
Yeah. Cool.
Thank you. I think we have time for one more. There's someone towards the back with their hand raised.
In relational databases, right, especially like Oracle, there are utilities which can recommend what sort of indexes an application can create based on the query patterns. So in Mongo, is there any utility which recommend any index to be created based on the query patterns?
Yeah, that's a good question. So this is always a little tricky, and we were really focused on the early phases of development where as MongoDB, we can't really observe your workload. But we have this feature called Performance Advisor, which is meant for once you're actually seeing you're observing your expected workload, and it looks at all of your slow running queries and recommends indexes based on your slow running queries. So I would definitely recommend checking that out. It is like, again, a use case you have to be observing the workload that you're expecting, so it's a little more reactive, but it's a good fallback tool if your use cases change or your planning up front wasn't actually representative of what you're observing.
Cool. Well, that's it. Thank you everyone for your time.
Thank you.